Imagine this. Amid the cold darkness, where even starlight barely pierces eternity, something crafted by human hands crosses the boundaries of the possible. It goes farther than anyone could have imagined, carrying not only instruments and antennas, but a fragment of our soul, encoded in metal and music. This story isn't about the future. It has already begun. At its core lies an event that happens once every few generations, if not less often. You'll never be able to look at space the same way again once you learn what exactly made this journey possible. What scientists and engineers did to outsmart time, space, and the laws of celestial mechanics. What exactly we sent into eternity, and why. Subscribe and like if you want to find out how humanity challenged infinity. The idea for the project emerged in 1964 when Gary Flandreau from NASA's Jet Propulsion Laboratory noticed that the rare alignment of the planets, Jupiter, Saturn, Uranus, and Neptune, in the late 1970s created a unique opportunity to send a probe that could use gravitational maneuvers to sequentially approach all these planets. In 1969, NASA formed a working group to explore the outer planets, which developed a program with two missions. One planned to launch in 1977, targeting Jupiter, Saturn, and Pluto, and the other in 1979 aimed at Jupiter, Uranus, and Neptune. This approach allowed the mission duration to be nearly halved compared to a single launch to all planets. Additionally, a new type of automated spacecraft was proposed, the TOPS thermoelectric probe, capable of operating for more than 10 years. However, in December 1971, Congress refused to fund the program due to its high cost, estimated at $1 billion. As a result, NASA was offered a scaled-down version, and the project was replaced by the more economical Mariner Jupiter-Saturn program, which later became known as Voyager. How were the spacecraft built to withstand the extreme conditions of space and the long-term mission beyond the solar system? What design solutions were applied in the development of the scientific and power equipment? And how did engineers manage to combine such complex systems into one spacecraft? The spacecraft was equipped with television cameras having a resolution of 800 lines, which used special Vidicons with memory. Reading a single frame took 48 seconds. The optical system included two cameras, a wide-angle camera with a field of view of about 3 degrees and a focal length of 200 millimeters, and a narrow-angle camera with a viewing angle of 0.4 degrees and a focal length of 500 millimeters. Additionally, the spacecraft carried spectrometers covering the infrared range from 4 to 50 micrometers and the ultraviolet range from 50 to 170 nanometers. It was also equipped with a photopolarimeter and a plasma investigation suite that included plasma detectors, low-energy charged particle detectors, cosmic ray detectors, high and low sensitivity magnetometers, as well as a plasma wave receiver. Since the spacecraft was headed toward the outer planets, the use of solar panels was impossible. At such a distance from the Sun, the radiation flux became too weak. For example, at Neptune's orbit, it was about 900 times weaker than near Earth. As a power source, 3 radioisotope thermoelectric generators operating on plutonium-238 isotope were used. At the time of launch, the total power of the generators was about 470 watts at 30 volts DC. What mysteries and unexpected phenomena did the Voyager probes reveal to us as they embarked on their distant space journey? Thanks to the Voyager 1 and Voyager 2 missions, humanity has greatly expanded its understanding of the geology of celestial bodies beyond Earth. Contrary to expectations, many moons of the giant planets, previously considered dead and geologically inactive, turned out to be surprisingly alive in terms of internal activity. The discoveries made during the probe's flybys were a genuine shock to astronomers. In the coldest corners of the solar system, volcanoes were found erupting materials hundreds of kilometers high, as well as entire seas of liquid hydrocarbons. Flying past Io in March 1979 at a distance of about 20,000 kilometers, Voyager 1 transmitted images to Earth that radically changed the perception of this Jupiter moon. Its surface was unusually bright, colorful, and most strikingly, almost entirely devoid of impact craters. Instead, high-resolution images revealed a fresh and geologically young surface, with pits of strange shapes, massive mountains, and flows of material resembling lava. Several months later, after Voyager 2's flyby, engineer Linda Morabito noticed a plume rising above the surface in one of the photos. More detailed analysis of images, including those from Voyager 1, identified 9 such plumes, convincing evidence of active volcanism. This activity, as it turned out, had been predicted earlier. Calculations showed that Io experiences internal heating due to orbital resonance with Europa and Ganymede. Data were also obtained indicating that Io's surface and its thin atmosphere consist mainly of sulfur and its compounds, and that a plasma torus composed of these substances surrounds the Moon. Despite a more distant flyby, Voyager 2 recorded surface changes that occurred within just 4 months and confirmed that most volcanoes remained active, except for one, Pele, which appeared dormant. The first close-up images of Enceladus were also obtained by these spacecraft. In November 1980, Voyager 1 flew past the Moon at a considerable distance, and although the image resolution was limited, the remarkable reflectivity of the surface and the near absence of craters were already evident. These signs indicated a young surface and possible recent geological activity. It was also established that Enceladus is located within the dense region of Saturn's E-ring, leading scientists to suspect that particles in the ring may originate from the Moon itself. A closer flyby by Voyager 2 in August 1981 provided higher quality images. They showed that Enceladus's surface is heterogeneous. Some areas are much more heavily cratered than others, indicating significant age differences between regions. Particularly striking was the contrast between the young, smooth areas of Enceladus and the uniform, ancient surface of another moon, Mimas. This conclusion was unexpected, as nothing suggested activity on such a small and cold body. However, Voyager 2 was unable to definitively confirm whether Enceladus's geological activity continues today, or if it indeed supplies particles to the E-ring. These and many other discoveries became possible because humanity approached icy and rocky worlds previously considered empty and unchanging for the first time. The Voyagers initiated a new understanding of the nature of moons and how complex and unexpected the life of distant corners of our solar system can be. Why did 2 identical spacecraft, launched only weeks apart, cross the boundary of the solar system under such different conditions and with such different results? What is really happening at the frontier between the solar system and interstellar space, and how stable is this invisible boundary? From April to June 2010, Voyager 1 crossed a region located between 113.5 and 115.7 astronomical units from the Sun, where the radial component of the solar wind velocity dropped to 0. To refine the data, the spacecraft was reoriented for the first time since 1990. Based on the information obtained, scientists concluded that in this region, the solar wind was deflected sideways under the pressure of the interstellar medium. By December 2011, Voyager 1 had reached a distance of 119 astronomical units from the Sun, approaching the so-called stagnation region. Here, the magnetic field strength doubled due to the compression of the solar wind material, which was slowed down and even began to move backward under the pressure of the interstellar medium. At the same time, the number of high-energy electrons of interstellar origin increased almost 100 times compared to the 2010 levels. From January to early June 2012, Voyager 1's sensors recorded a 25% increase in the flux of galactic cosmic rays. These particles, which are high-energy charged elements of interstellar origin, indicated the spacecraft's approach to the boundary of the heliosphere and its imminent crossing. On July 28, 2012, at a distance of about 121 astronomical units from the Sun, Voyager 1's instruments detected a sharp decrease in particles and cosmic rays associated with the heliosphere, accompanied by a simultaneous increase in the intensity of galactic cosmic rays. Although the measurements soon returned to previous levels, such changes repeated 5 times, and after August 25th, there was no return to the earlier state. It was expected that crossing the heliopause would be accompanied by a change in the magnetic field direction, but only a change in its strength was recorded, without significant change in orientation. This raised doubts about whether the spacecraft had actually crossed the boundary of the solar system. The discussion continued until September 12, 2013, when a team of researchers led by Donald Gurnett published data on plasma oscillations around the spacecraft. The measured electron density corresponded to values expected in the interstellar medium. Despite the absence of a change in magnetic field direction, it was acknowledged that Voyager 1 had exited the heliosphere approximately on August 25, 2012. In 2018, Voyager 2 joined its brother, reaching the boundary of the solar system at a distance exceeding 119 times the Earth-Sun distance. Researchers noted that the transition from the solar system to interstellar space could have taken less than a day. The spacecraft crossed the boundary during different phases of the solar cycle: Voyager 1 during solar minimum, Voyager 2 during solar maximum. Due to these differences, conditions at the boundary varied significantly. While in the case of Voyager 2, solar material partially leaked into interstellar space, Voyager 1 showed the opposite phenomenon. Interstellar particles penetrated inside the heliosphere. Scientists hope that further data analysis will help understand the mechanisms by which particles can overcome the gravitational and magnetic boundaries of the solar system. What would you tell about humanity if you could send only one short signal into the universe? Could a message created by humans and attached to probes be understood by beings whose nature and perception are unknown to us? The Voyager Golden Record project cannot be called a whim of engineers or a caprice of scientists. It was backed by serious, carefully organized work under the leadership of Carl Sagan. The team, bringing together specialists from various fields, including representatives of art and culture, faced an almost impossible task: to create a universal image of humanity that would be understandable even to beings who had never known Earth. A special information carrier was sent into space, a blend of visual and sound fragments intended to tell our story. It contained 116 images selected to reflect the diversity of life, landscapes, animals, people, as well as diagrams explaining the chemical composition of substances. Accompanying them were 12 minutes of sounds capturing birdsong, whale songs, wind, surf, thunder, everything that conveys the atmosphere of Earth. The presence of humans was emphasized by voice greetings in 55 languages, children's laughter, footsteps, brainwaves, an address from the UN Secretary General, and a message from US President Jimmy Carter. Additionally, the record included encoded information. The music included in this message reflects a desire to show the richness of human culture. It features works by Bach, Mozart, Beethoven, Stravinsky, as well as melodies originating from China, India, and Azerbaijan. This was an attempt to demonstrate that culture is not confined to the boundaries of one civilization, but exists in a variety of forms. However, not everything went smoothly. Folklorist Lomax opposed the inclusion of Johnny B. Good, considering rock and roll too teenage. Carl Sagan countered by reminding that teenagers are part of humanity and their culture deserves to be heard. There was also a debate about the depiction of a naked human. Instead, silhouettes were chosen, and anatomy was shown through the evolution of vertebrates. Interestingly, no Beatles songs made it onto the record. The reasons remain unclear. One theory suggests it was due to copyright issues, supposedly difficulties with EMI over the song "Here Comes the Sun." But other project members claim that the song wasn't even considered. It is noteworthy that John Lennon himself recommended the sound engineer for the project. Furthermore, on an empty part of the record, an inscription is engraved in honor of all music creators. But what if the golden record isn't really made of gold? What is it actually made of? Although called golden, the record is actually made of copper and aluminum. Gold is present only as a thin protective layer, emphasizing the symbolic rather than material meaning of the project. Will those who find this message understand us? The purpose of this message is not merely to preserve information about Earth, but to attempt to establish contact. Whether it will ever be heard is unknown. Yet, as one of the engineers said, working on the project felt like sending children off on a journey, leaving home but remaining part of you. This record became a keeper of hopes sent into infinity, and today, continuing its journey through space, it remains a symbol of humanity's desire to understand who we are and whether there is someone who can hear us. Will other civilizations ever discover the Voyagers and unravel the mystery of their origin? What will space be like millions of years from now, when even the sun has faded and the devices we created still drift through its dark depths? Given that Voyager 1's speed exceeds that of its counterpart, it will be the first to reach a distance of 1 light-year from the sun. This event will occur in approximately 20,120 years. Around the year 40,000, our space probe will encounter its first star, Gliese 445, passing by it without coming closer than 1.7 light-years. As for Voyager 2, according to NASA data, in about 40,000 years, it will be 1.7 light-years away from the star Ross 248. Then, roughly 296,000 years later, it will pass at a distance of 4.3 light-years from Sirius, the brightest star in the night sky. Scientists believe the probes will leave the boundaries of the solar system between 28,000 and 80,000 years after launch. After that, they will be held by the gravity of the Milky Way. The probes will begin a long journey orbiting the center of the galaxy, rotating together with the Sun and other stars. They will complete 1 full orbit around the galactic center approximately every 200 million years. In order to escape the gravitational pull of the galaxy, the probes would need to reach speeds of about 330 kilometers per second, which is extremely unlikely. Therefore, they will remain in orbit around the center of the Milky Way for a very long time. It will take billions of years before high-energy photons gradually destroy Voyager 1 and Voyager 2. However, the possibility of collisions with asteroids cannot be ruled out, which could lead to a much earlier demise of the probes. But if such collisions are avoided, it is imaginable that the probes will continue their journey through space, long after the Earth, other planets of our system, and even the Sun itself, which will eventually fade and become a white dwarf, have disappeared. Subscribe to the channel and stay tuned for news to not miss fresh discoveries, amazing stories about the Voyagers, and the future of distant space travel.